Hey everybody, welcome back. Today we're going to talk about relays. They're probably one of my favorite industrial components, and it's not because they're very fancy. In fact, kind of the opposite. They're a pretty simple device, but just the way that they're used creatively and the different ways we have to implement and troubleshoot them can just create some really fun circuits to play with. So I'm just going to give you a little bit of an idea of what a relay is and what it does. I can't possibly show every kind of relay and all the different applications because they're found in everything from industrial use, automotive use, and everything that has electronics in it probably has some sort of control with relays. Now they were largely, or at least started beginning to get phased out with the implementation of transistors, but now there's been decades that transistors have been in play, but relays still offer us a few things that transistors don't and likely never will be able to completely replace. So that's why we still see relays in use today. So just to give you a little bit of an idea of the different sizes and shapes they can show up in, relays are all an electromechanical device, which means that they run on electricity, but they actually have some sort of a mechanical component in them as well. When a relay trips or activates, energizes, you can hear a little bit of a click inside of it. It's a little metal tab switching from an open to a closed position, kind of like a light switch. When you reach over and click a light switch on and off, you can hear a little bit of a clicking, toggling inside of it. That's going to happen electrically inside here. So it's actually a mechanical switch. One of the disadvantages then, if it's a mechanical switch, you can only flip a mechanical switch so many times before it breaks. Kind of like if you had a paper clip, you can only bend a paper clip even a little bit. You can only bend it so many times before finally it breaks in half. And any kind of metal, if it's moving, it's going to do the same thing. It's going to be subject to fatigue, which is a repetitive action. Now they do design them to last for a very long time, so if used properly, they'll probably last a lot longer than the life expectancy of whatever device they're running in. But this is a little tiny relay. You can see from the bottom of it, kind of turn it here a little bit, there are 5 pins on the bottom of this one. So I'll show you in a minute how you can count the number of pins and kind of get an idea of what kind of relay you might be dealing with. Here's one that's slightly larger. You can see on the bottom of it, there's now 8 pins on this one. There's 2 that are kind of off by themselves way up here at the front, and then there's 2 sets of 3 way down here at the bottom. Those groupings of 3 and the 2 by themselves are pretty important. Here's another one that sometimes they call the ice cube relay. This is an ice cube relay. You can see on the coil, there's a thing that says, spin around here, it says 24 volts. DC24V, DC 24 volts. Industrial control voltages, 24 volts AC and DC is really common. There's also some that are 120 volts AC. I don't have any of them that are 120 volts, but you'll see it printed on the plastic around that the same way. Here's another one that actually, surprisingly, is exactly the same setup. Look at the end of this one. You can see these 2 little bright copper metal tabs inside of it. That actually shows you the number of circuits inside of the relay that are able to be activated. This one's obviously quite a bit larger, but if I show you the same end, it's the same setup, 2 copper tabs. The pin style on the bottom is a little bit different, but you can still see they kind of have the same general idea of the pins, but there's 8 of them, just like there were in this one. So the size and shape may be different between all these relays, but very often the capacity is the same. The number of devices that it can run is the same. Here's one that's even larger. I'll pull it out of a socket there. So you can see the pin style on the bottom. The shape of the pins is about the same. Big solder lug style connection there. But this one has 2 pins down here at the bottom, and then instead of just 2 groups of 3, we see 4 groups of 3. And the number of copper tabs, 4 different circuits that can be activated by this. The number of circuits that can be activated, like 2 versus 4, is the number of poles. So this one we'd call a double pole or a 2-pole relay. Here's a 4-pole relay. When you see the relay with the little groups of 3 pins, the number of groups shows you how many poles it has. Now there'll always be these 2 by themselves. On different relays, they'll show up, the groupings will be in different places, but I've got a little group of 2, and then 1, 2, 3, 4 groups of 3. It's a 4-pole relay. Here's one that's a little bit unique, but actually I like it because it shows you one of the real fundamental components of a relay, and that's the coil. Coil is extremely important to understand in terms of a relay. This one has a coil, but it's hard to see. Can't really tell. This one has a coil as well, but it's wrapped in tape. So I mean, if you know what you're looking for, you can tell that that's a coil. But this one, when you look at that, you say, ah, that is a coil of wire for sure. So induction, every time we see a coil, we can go back to induction. I've done lots of videos about transformers and inductors and things like that. So every time we see a coil of wire, we see induction. Really important principle here is that when current travels through a coil, it generates a magnetic field, or effectively we're creating an electromagnet. Electromagnets are specifically designed to attract metal. Now the metal in this case that it's trying to attract, if you look at the side image of this really close, get it in focus there, maybe. There's a little tiny copper pad down here at the bottom, a couple of little contact points. And as the coil activates, it pulls on this big metal flap right here. When it pulls on the metal flap, the copper tab will switch from the contact that it's touching right now to the contact on the other side. And you'll hear a click when it does that. As soon as you apply electricity to the two correct terminals, called the coil terminals, the click will indicate that it's pulled in on that big metal flap, this big metal flap right here, and that the copper contacts have switched from one side to the other. It's a big click. The larger the relay, typically, the more mass it has to move, and the louder the click is going to be. The bigger the mass that it has to move is usually indicative of how much current those poles are able to move. And look at the size of the copper tabs on those. They're pretty beefy. Looking at this one, it says for a 120 volt system, just looking at the ratings on the back of it here, it says capable of handling up to 15 amps. So that's a pretty large circuit, 15 amps that this is able to handle. Now, if we look at transistors, transistors can handle 15 amps, but you usually have to get a pretty massive transistor in order to accomplish that. They're also a little bit more difficult to use. Now, all of these relays, they have two terminals that are for the coil, and then another set of three that are used for what they call the contacts. A relay has coil, contacts. You get to turn the coil of a relay on and off, but when you do that, it switches over the contacts. So the contacts are like the reaction, the coil is the action that you take. Very often they'll call those inputs and outputs. A coil is an output to a control system. So when you press a button, you can activate the coil. The button is the input, the coil is the output. But then if you think about this as a button, it's just a button that's controlled by electricity instead of somebody pressing it. When it's activated, it turns on a circuit, or basically it becomes the input to a separate system. So they call it a relay, kind of like a relay race. You're running along, and then when you get done with your part, you hand off something like the baton, you hand it off to somebody else. And they're a completely different runner. They're running a completely different race than you were. It's just what you did was then handed off to them so that their action was a response to your action. When we activate the coil of a relay and the contacts switch over, we're then able to do one of two things with that contact side. Either we can allow a circuit, a separate control type circuit, to turn on when we hear that click, or we can allow it to turn off when we hear that click. The set of three contacts, so this one has three terminals that are indicating the contacts on the bottom, three on this side, three on that side. There's two copper tabs, so one set of three goes to one set of contacts, the other set of three goes to the other set of contacts. That set of contacts has a common terminal. It also has a normally open terminal. That's the middle one, and you can tell because there is an air gap right in there. So it's not connected to that terminal, but this copper tab is connected to the furthest outside terminal. That means that while it's sitting here, unenergized, obviously I'm not powering the coil of this right now, I have an electrical connection between this one with this white wire that's looping up over here and this terminal on the very outside. That's called normally closed because right now the circuit is being connected even without it being energized. If I energize the coil and I hear that click, now this white coil, this white looping wire, is going to then be connected to the middle terminal, the inside one, when it switches over. So that's what we call our normally open set of contacts. So relays have coils, they have contacts. The coil is the rated voltage of the relay. So I'd call this a 24 volt relay. It doesn't indicate how much voltage are on the contacts. I really don't know that. But I do know that it's going to take 24 volts to run the coil. If I try to run more than that, like if I accidentally plug this into a 120 volt system, I'm probably going to destroy the coil. So be very careful that you've used the properly rated coil. This one's a little tougher. Got to read the fine print because I don't have tape wrapped around that to just say, oh, it's 24 volts or 120 volts. Now if I use too little voltage, Like this one should be, let's see, yeah, 5 volt DC. Maybe can't even read that. Focus is tough. 5 volt DC. So that means that the coil is going to be activated with 5 volts. Now, if I found one that was the same shape and size, but was run on 24 volts, and I plugged that in, I'm probably not even supplying enough voltage to activate the coil. So it wouldn't operate. So if you need one with lower voltage and you plug in a relay that's rated for a higher voltage, nothing's going to happen. But if you have a higher voltage and you plug in a relay that's rated for a lower voltage, probably going to smoke the relay, and it's going to be done. Now, a good, easy way to test these relays, if you have a multimeter around, is just change it over to the resistance setting. So this one I've changed it down. I'll start with the 2 kilo ohm range just to see. Might have to turn that one down a little bit. And I'm going to connect the 2 leads on this one to these 2 terminals. Usually the 2 that are off by themselves are the coil terminals. And I see 0.649 kilo ohms. So that's about 650 ohms of resistance for that coil. Considering it's a 24 volt relay, 650 ohms, we can use Ohm's law to figure out how much current that is going to consume. It's probably not going to be a whole lot, but relays are going to consume a whole lot more current than most other solid state devices. So we have a circuit that can be controlled electronically. It's a little bit slow. It can't operate as many times. It can't switch on and off as many times as a transistor can, but they're very versatile devices found everywhere in industrial electronics, and they're a really handy device to design different logic sequences and to be able to turn big loads on and off without having to have those loads directly running through all the push buttons that you're operating. I'll have plenty more videos on how to connect these into circuits, what the different things like these, the sockets that they plug into, how to test the contacts on those. There's all kinds of different things there. Lots of fun on those. Relays have a lot of information behind them, but this is just a little bit of a survey of what they look like, kind of how they operate, and some of the different characteristics that you see within them. So hopefully you had fun with this one, and there will be plenty more. Trust me, we have a lot of stuff to cover on relays. So thanks, and have a great day.